There we go. So I'm actually going to record all these classes and upload them to my website. So if any of you want to come back and view them, you can. And then also, if for some reason you can't make a synchronous class, message me so that I'm aware. And then you can obviously watch it. I'll have them all uploaded so that you can watch it. But please let me know if you can't make a synchronous class. Please let me know just so I'm up to date. And then your final exam is actually another GitHub repository. And so the process that you went through to, get your other GitHub stuff set up, you'll do that for your final exam, where you'll basically like go to GitHub Classroom. It'll give you a link. It'll create a repository for you. There'll be assignments within there. You'll submit one pull request, and then that's your final exam. So final exam is taken care of. The only thing I have to think about is your final test. But as far as that concerned, stay in contact on Slack. I mean, keep using the Slack team. I think you guys already know this, but you can go to citadelcs.slack.com if you don't have the app installed. Let me see if this. I have 1,000 Slack teams, so let me see if I can find which one it is. Slack, Citadel. And it has the same view as the app. So if you don't want to download the app, you can actually download, or you can actually access it within a web browser like this, okay? Let's see, guys. Sit, learn, syllabus here. That's the plan I was talking about. And then this is a link to class recordings, which is, I'll have them on my site, and since there's none there now, but they'll all be listed out. So if you miss class, they'll be here for your viewing. All right, questions? I know that's a lot. None? Everybody looks thrilled. Kind of sucks that you guys are finishing out the semester like this, I know. So just, jumping with the schedule, we'll just kind of get going into it. So we're going to keep with the schedule. I've kind of buffered some time on the end here. This April 20th week, I call it Programming Assignment Workshop. Basically, if there's any programming assignments, any of them, assignment 1 through whatever that you have trouble with, I actually won't be teaching anything new that week. So April 20th, I won't be teaching anything new. That will be review for final exam, and just hop on, and if you have questions about assignments, you can use that week, okay? Now, don't wait until the final minute to do your assignments, obviously, but use that week to ask me questions about stuff, okay? So we'll dig into it, and we're cover new material and everything. We got a couple weeks till we think about test 3. We do have some programming assignments coming up. In a week, you'll have programming assignment 7 due, and then next Friday, not this coming Friday, but the Friday after that, you'll have programming assignment 8 due. So we'll keep rolling through it, but just think about this week if you're having issues with anything, okay? Also, test 2 is in Sit Learn, if you want to view that. And I have, here they are, actually, I have the grades. See. Yes, so I always call it top 2, Andrew McNay, big 98. So you're the top guy. So everyone got 2 points. And then numero dos was Cyrus with a 96. Okay, so congrats, guys. All those grades are in Sit Learn. I would scan all these. That's a lot of scanning. But if you actually want your test, let me know, and I will mail it to you. If you don't, just don't worry about it. I will shred it. But those grades are in Sit Learn for you to view. So yeah, if you have any questions like this, so just kind of keep this in mind. This will kind of be our syllabus going forward of what we have. And then click down here at the bottom, class resources. This just kind of takes you to all the class resources, but here is you guys' class, and class recordings will be here, okay? So that if you need anything, that's the easiest way to get to the recordings. if that is it, we'll dig into our new topic, which is recursion. Well, first, let's look at program assignment 7, okay? So let's see, yes, attack. So today I'm assigning assignment 7, and then let's see, assignment 7, and then 1 week from today, assignment 7 is due. Okay. All right. So assignment 7. Look at, and I can actually send you guys a README on how to run JavaFX that I've written out. But remember, for JavaFX, you have to like change that POM file, which is really weird. So I'm going to also pull up my Computer Science 202 project here. Okay, let me put it on screen 2. Okay, can y'all see my code? Yes, yes. Okay, I see some nods. All right. So let's go to JavaFX. So within JavaFX, if you want to run JavaFX with IntelliJ, it's so old. You can't just, on previous assignments, you could just kind of run by the play button. You can just, hey, run or debug or whatever. You can't do that with JavaFX. So what you actually have to do is come down to your POM and actually change this main class here. Okay, so this is a plugin within JavaFX, within Maven, that allows you to run JavaFX applications. So you actually have to change the main class here to whatever JavaFX class that you want to run. And then you come over here on the right-hand side where it says Maven, plugins, JavaFX run. Okay. If it doesn't show up, just recycle, refresh it or whatever, and then it will show up. And then what that does is that Maven will do the work of compiling the class, putting the JavaFX jar on the class path, and all that mess that you don't really want to do, so that it can actually execute a JavaFX program. So just keep that in mind. But the reason why I say that is what assignment 7 is. Okay. So assignment 7 is you're going to finish the program black and blue button to change the color of a circle as when the mouse is pressed, and as black when the mouse is pressed, and as blue when the mouse button is released. So it'll look like, click black, blue, click black, release blue, that type of thing. Okay. So that one is here at the top level. It's just an empty class. So there's a lot of examples within your code base on getting that set up. Remember, you have to extend application. An application is a JavaFX class, and then it will give you a start method. And then that's where you do your stuff. But you also need that main method where you call launch. So just look at the examples within your code base, okay? So that's the first part. So you have black and blue button. That one is pretty simple because I think there's a good bit of examples within the code base that you can do that, okay? Second one, finish the program investment calculator, okay, to calculate the future value of an investment at any given interest rate, for a specified number of years. The formula for calculation is, got hiccups. Future value equals the investment amount times 1 plus interest rate, years, times 12. I don't know if you can see all that through my screen, but this is basically your formula that you're going to use to calculate this number here. So what you'll have to do is create a little UI, a little JavaFX UI that shows, label, text box, label, text box, those type of things, label, text box, on down. And then when you hit calculate on, when you click that, that will be your event that triggers the calculation of this formula. So you'll pull this value, this value, this value, do your formula here, and then you'll place the future value in here. Okay. So that's really it. But there's a lot of examples within JavaFX that within your repository that show you kind of how to do these different types of setups. Okay. So if you have questions, let me know. And you guys remember, you guys can work together on like the Git stuff, and you can even work together on thinking through the flow, like your algorithm flow and stuff. You just don't copy each other's Java code. Okay. So if you guys get together and you're like, okay, this is starting to stink, like I don't know what's going on, let me know, and we can do like a synchronous Q&A one evening or something like that all together rather than one-on-one, or if you want to do one-on-one, that's fine. But so just keep that in mind. We can always do it that way. So assignment 7 assigned today, and then it will be due, so today's 23rd, it'll be due March 30th. Okay. And then we'll go over the rest of the stuff. We'll go over assignment 8 on Friday. All right, questions? Any questions? Still good? I see head shakes. Still good? All right. So we're going to dig into recursion. All right, recursion is going to, if you've never dealt with or seen this before, it will take a little bit for your mind to kind of get wrapped around it, okay? So let's see. Yeah, so this is kind of the use case. Okay, suppose you want to find all the files under a directory containing a particular word. How do you solve this problem? And so what they're basically introducing here is in a file structure, and this is just a use case, but recursion applies to more than just files. You don't know from the top level, you don't know how many files are in that folder or how many folders are within that folder and how many folders are within those folders. And so you can see, like at the top level looking down, you don't know what your actual folder structure looks like. So if you were going to go through this and try to, I mean, you could do it in for loops and while loops and, you know, this, that, but then your code gets kind of hard to maintain. Like it gets kind of hard to actually look at what you're doing in your loops. So recursion is basically simply calling a method within itself. Okay, so you can see how that kind of turns your brain inside out, but you are calling a method within itself. Okay, we lost somebody. All right, suppose you want to follow that, so let me just show you this. All right, so this is an H tree. An H tree almost looks like a car or something like that. Design plot. So how do you write a program to display H trees? And so what this is showing is that this is an H tree, and then this H tree has an H tree, and then this H tree has an H tree and H tree. So you kind of see the ordering of it. So you can actually use recursion for something like this, where you write the method at a base level, and then whenever you call it, you can just specify how many orders or how many levels you want to display this, and then it will show it. So let me just kind of dig into some of the examples. Computing factorial is actually probably the simplest base case how to show it. So whenever you do factorial, so if you do factorial of 0, factorial of 0 is 1, right? If you do factorial of whatever number, basically it's n times the number before it. So factorial is, you know, factorial of 3 would be 3 times 2 times 1, or factorial of 5 times 4 times 3 times 2 times 1. So this example of computing the value before it. I think this is the animation. So yeah, so if I was wanting to do factorial of 4, what that would be factorial of 4 times the factorial of 3. And then if I keep going, it would be 4 times 3 times the factorial of 2. 4 times 3 times 2 times the factorial of 1. 4 times 3. And so you get the kind of the tree structure here of what it's building. And then once you hit all the cases, it starts to bubble back up. Okay, so that's one of the things about recursion, is that it's easy to maintain code. Like it will actually show you you'll write much less code to accomplish a larger task. But what ends up happening is it will build your JVM stack. So it will, every time that you do a recursive call, it puts this method on the stack. So boom, boom, boom. So if this was factorial of 100, you can think of that. You would have 100 or so calls on your stack, and it's not until you hit the very base case until it actually starts to bubble back up. So you'll see like this parabolic view of your JVM of just like, okay. And this is just another example of that. So let me see if I can find some recursive examples. Compute factorial, okay. All right, so this is really the factorial method here. So this is just a main method to spin up, you know, take in a non-negative integer and all that stuff. So this is the factorial method. This is the recursive method. So there's two facets of a recursive function, and one of them is the recursive call. So here you can see like this is the factorial method, and I'm actually calling it within itself. So it's the recursive call, and then the base case. Okay, so the base case says once I hit this case, that triggers that bubble up effect, if you will. If you don't have the base case, this will just go off into affinity. Okay, so we know that factorial of 0 is 1. Okay, so if you do factorial of 0, it equals 1. So that's an easy base case for us. So if we ever get to n equals 0, just return 1. However, if not, if we want to say factorial of whatever, you would say that number times factorial of basically the number before it. All right. And so anything that can be accomplished in recursion can be accomplished in a for loop, can be accomplished in a while loop, can be accomplished in any of those loops that we already have within Java. But what factorial does is it allows you to write much less code, as you can see. I mean, this is 5 lines of code. It's very easy to read, and it accomplishes the same solution. You just have to be careful. Recursion is not a silver bullet. There are some cases where you just want to write it in a for loop because of the efficiency. I mean, sometimes recursive functions, if you start calling them, putting a lot of methods on the stack, it will actually kill your it will actually kill your performance. So anyways, just keep that in mind. So this is basically the perfect use case of that. So let's just run this. Let's debug it and see what happens. Let me put a breakpoint. Let's run it. All right, in a non-negative integer, so let's do 5. All right, so here's base case, right? Base case is n equals 5, so we're not going to hit that. And so what we do is we actually hit the recursive function, which will be 5 times factorial of 4. When we do that, now we have 4. And what you can see over here, this is my actual stack, if you will. Every time I do this, I have a factorial function call on the stack. So now it's factorial 4. So now it's 4 times factorial 3, going back up, and you can see this stack just continuing to grow. Now here's factorial of 3 times factorial 2. So come in as 2. You can see just the value of n right here each time. Here's factorial 2 times 2 minus 1, 1. So here we're at factorial 1. Factorial 1 is 1 times factorial of 0, which is 1. So it's not until I hit this return statement that then you'll see all these methods over here on the left-hand side that's on the stack just start to return, start to bubble up. So they return that one gets plucked off, that one gets plucked off, that one gets plucked off, boom. So now our input was, oh, that's the scanner. Let me skip on down. So now here is my value, 120. So if you do factorial 5, it's 5 times 4 times 3 times 2 times 1. So do some simple math. 5 times 4 is 20, times 3 is 60, times 2 is 120, and then times 1. Okay? So that is the correct value of that. So let's kind of just do some stress test, if you will. So I'm going to run it, and I'm not actually going to debug it. I'm just going to run it. Let's do 5. Okay. So factorial 5 is 120. That didn't take long at all. But let's do some just ridiculous number. Let's do like 10,000. And see, actually, the reason why this blew up is because the integer, or excuse me, the long value is actually not big enough for that. So I think I kind of crashed it on accidentally. Let's try something a little bit smaller. Maybe 50. Yeah, I'm still crashing it. I'll have to change this to big int or big long or something like that to show you. But basically what I was trying to show you is that anytime you do have a lot of recursive calls on your stack, you'll actually see a performance overhead. You'll see that method kind of quiver for a minute and then it will return, which in computation time is really not that bad. But excuse me, in human time it's not that bad, but within the computer it's actually really slow. So if you were doing large numbers, it would actually be easier to do this via like a for loop or something like that. Okay. So we'll just kind of keep going through the slides. And feel free to hop in with any questions at any time. So this is just showing the trace, and so each time that it calls, it puts these on a stack, and then once we hit the base case, you'll see it bubble up, bubble up, bubble up, bubble up. Okay. And so this is what I was just talking about, the space required for factorial 4, 3, 2, 1, 0, and then it bubbles back down. So it's just something to keep in mind. The two things you need to understand though is for a recursive method is the recursive call and the base case. Recursive call, base case. Okay, so if you miss either of those, you're going to kind of mess up. The base case is very important because if you do a recursive call and you don't have a base case where it can actually cause that bubble up effect, you would then just blow your stack up and it'll go on to infinity. But if you don't have a recursive call, then obviously it's not a recursive method. Okay? Here's another one. This is Fibonacci numbers. So Fibonacci numbers are basically the two numbers previous to it added together. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8. So you can see that. So this is the Fibonacci series, and this is the index. So pretend this is kind of in an array. So that's what's going on here. So let me show you this one. Where's it at? Fibonacci. Okay, so this is the Fibonacci. This is actually the recursive call for Fibonacci. So this one actually has two base cases, all right, because you actually need both of these base cases in this one. But this one has two base cases where if it equals 0, you return 0. If it equals 1, you return 1. Other than that, you would do Fibonacci of index minus 1 plus Fibonacci plus index minus 2. So basically, this call here is if it's not 0 and I'm not returning 0, and it's not 1 and I'm not returning 1, then it has to be the two numbers previous to that added together. Okay, and the reason why you have two base cases here is because you have two recursive calls here that are dependent upon each other. Okay, that makes sense? Makes sense. Okay, so this one, let's do a small example of this one. To debug this one. And we'll probably bounce out around like 840 just to kind of give you guys some time. I know this is kind of a weird normal that we're getting into, but anyways. All right, 8, let's do 8. So what we're doing here is we're going to bounce into that. So it's obviously not that base case. It's not that base case either. So we return, what this will actually return is the Fibonacci of 8 minus 1, so Fibonacci of 7 equal to Fibonacci of 6. Okay. So that's actually what that returns. Whenever I do this, I get two methods on the call stack. Same here and here, and you'll see each one bubbling up. Okay, so we're going 4. I'm just going to kind of walk through this and I'll talk through it. Here we are, 3, 2, 1. All right, so now we hit 1. 1 is the base case. We return 1. So it returns that one, which is index of 2. And so this is index of 0, return 0. And what you'll actually see is it may be out of order, but if I was able to draw the actual tree, there's multiple fib methods that need to go on the stack. So if I did Fibonacci of 8, actually, let me see if I could. See, new share. I think I have a whiteboard. Check this out. Goes in. Can y'all see that? Can y'all see a whiteboard? Sweet. Let's see if I can draw. Draw. Okay. So I'm gonna try this. Let's just say I did 8. So 8 would go to. Man, I'm terrible at this. What is 8? 7, 6. Actually, and then 6 would go. I'm going to try to do it small. 5, 4, and then 4 would go to 3, and 2, and then 2 would go to 1, and 0. Okay, so you see that? That is actually just, do you still see that whiteboard? Oh, you can't see the whiteboard? No, what happened? Resume share. Can you see that? Oh, nice. There we go. Okay, so this is actually just like one leg of the tree. All right, so this is like if I were to do one leg of, so 7, 6, 5, 4, 3, 2, 1, 0, and this is my base cases here. But if I were to do this one as well, so I would have 2 and 1, right? So this is a base case. So I actually would have multiple fib calls per tree thing, right? So this is a base case, this is a base case, this is a base case. If I did this one, this would be 1 and 0, that one there. This one would be 4 and 3, and this one would be 2 and 1, and 1's a base case, and all that stuff. So as you can see, whenever you have something like Fibonacci that does multiple recursive calls, you can really blow your stack up really quickly. So something like this would be good for maintaining code for small numbers, but if I were to do something like 100, just something simple, it would take forever. And actually, I think I can share that. I'm going to stop sharing that. All right, can you see my screen? No, can you see me? I guess you're seeing me now. Let's try this. There you go. You can see that. Okay, so now let's just do this. Let's just run it through. I'm running it, not debugging it. So if I run it with 8, 21, that's pretty quick. But if I were to run this with like 150, I mean, 150 is a small number for a computer. So for it to take this long, and it's just sitting here just chugging along, that goes to show that fib or recursive calls may not always be the silver bullet when it comes to a program. You can see I did all this in 6, 7 lines of code, but it's taking seconds to compute, which is not good. So for something like that, you may want to actually change it to like a for loop or something like that to get an actual better processing. Okay, but I'll cut that off. That's just kind of show you that can be done, but it doesn't mean it should be done. Okay. So here's just the slides for fib numbers going through it, and you can see how there's multiple times you'll hit a base case. Now the JVM doesn't actually like cache the base case where you're like, oh, I know what this value is, I know what this value is, so I don't need to call this twice and put it on the stack. It doesn't know that, so it actually will put all of these methods on the stack. And then this is just kind of the two characteristics. I'm kind of getting ahead of myself, but yeah, they should have one or more base cases, which is the simplest case, and that's used to stop the recursion. That's used to actually cause the bubble up. and then every recursive call reduces the original problem. So this is with you're reducing the problem. If your recursive call doesn't actually take your problem to a smaller problem, so like Fibonacci at 8 takes it down to 7 and 6, and 5 and 4, and 3 and 2, then your recursive call isn't actually going to go in a direction towards your base case. Okay, so not only should you have a base case, but your recursive call should take a step in the direction of your base case. If that makes sense. And then this is just some examples using problems. And also think, and I think I told you this before, but one of my first job interviews was I had to do a palindrome detector, and it's very easy to do it with recursion. However, if you cause your recursion to actually pass itself, so a palindrome is the same as a word that's spelled the same forwards and backwards. So if you actually were to get it to pass itself instead of stopping in the middle, then your recursion doesn't actually help itself, if you will. So palindrome is actually a really good example, because what's going on here is I'm checking to see if it's less than or equal to 1. If I have a string that's 1 length, then it's of course a palindrome because it's just 1 character. The next base case is I'm checking to see if the character at 0, or at the beginning, is not equal to the character at the end. So if I have a word like race car, that's an easy palindrome. R and R, beginning and end, they equal the same. So I'm not going to cut out. I'm not going to define that as false, because it still could be a palindrome. So that's when I come down to the final palindrome call method, where what I do is I actually cause the problem to be smaller, and I substring it. So what I do here is I actually chop off the first character at the beginning and the first and the last character. And then I call is palindrome again, and I do the same checks. So your base cases here, check if it's 1, check if they're not equal at the end, and then your recursive call actually reduces the problem. Okay. Recursive helper methods. This is just another slide. Selection sort. I'll go over this a little bit, but whenever you get into 223 in those classes, that's when Dr. V will actually talk more about algorithms and sorting and data structures and those type of things. You're going to do so many sorts and stuff like that. You're going to be blue in the face. But that involves a lot of algorithmic design, and one of which is recursive within sorting. So not only selection sort, but binary sort. So see if I can share this this whiteboard again. All right, can you see that? Here, all still see it? Okay. So basically, a binary sort is you have bubble here, bubble here, bubble here, bubble here. So just trying to get like a binary tree going. Okay. Let's see if I can actually, now that I've got this, let's say this is 25. This would be 30. This would be 35. This would be 37, 40, 42. Gosh, terrible drawing. 16. Okay. So this is an example of a binary search tree. And basically what you would do is, as you're creating a binary search tree, you say you want to put a number, you're putting things in a list. And the number to put in the list is 17. So what you would do is you'd start at the root, and you would say, is it greater than or less than the root? It's less than. So then I go to the left. Is it greater than or less than the root? It's greater than. So I would actually create a bubble here and call it 17, right? So that's how you would actually create the tree, but searching the tree makes it really easy, because you say, okay, I'm looking for 42. You would say, okay, is it greater than or less than the root? It's greater than. So whenever you traverse to the right, you actually reduce your problem in half, because you cut off this entire tree. And same thing. Is it greater than or less than this root? It's greater than. Go to the right, and I actually cut off this entire tree. So this is just kind of showing that recursive nature can go through searching as well. Okay. Step 2. Oh, it's 8:40. Okay, it's 8:40. We got plenty of time, so I'm not going to push it all the way to 8:50. Questions? Feedback on Zoom. I know this is a new weird normal that we're in, but since we're the 8 a.m. class, we're going to get real close real quick, like I said. So don't feel weird drinking coffee or sitting in bed. I know it's early. I'm shocked that I'm still up right now. But just stay in Slack. I'll keep in touch in Slack with any kind of updates. Use this channel. I know I've used it for mainly updates, but you guys can use it to chat. You can always obviously message me directly. And then I'll keep stuff updated on SitLearn and all that good stuff. Okay. So see you back Wednesday, 8 o'clock. Good. Good. All right. Thanks, guys.